subtract that. Okay? Let's get back to the cross product.
Okay.
So now for cross product, I think what I'm going to do for cross product is I'm going to actually do a specific example first. Two vectors with numbers in them, and I'm going to do the cross product by hand. And then after that, I'll do it for like general vectors. Because I think it would be easier just to see the numbers and how they work together. And then afterward, give you the general formula. So let's say we want to take, let's let u be equal to the vector. I'm sure there's an example here in my notes. Yeah, there we go. Let's just do that one right there. So we're going to cross those two vectors. See them? U cross V. So what you do first, what I like to do first, is I like to write the u vector first. 2, -3, 5. Okay? And then directly below that, I write the other vector 4, -1, 3. All right? Now, I'm going to start getting the answer. So the cross product will be equal to a new vector, right? It's going to have 3 components to it. Here's how I get the first component. And I'm going to help you by reminding you this is going to be the first component, this is the second component, this is the third, right? We just need to find those 3 pieces and we're done. So to find the first component, what I do is I come over here to this and I cover up the first column of numbers with my hand. Don't ask why, because this mechanically is the way it works the easiest. All right? Cover this up, all right? And you see those 4 numbers that remain? Mm-hmm. Do the determinant of those 4 numbers. Treat it like it's a matrix.
All right. So
okay? So it would be -3 times 3, which is
-9.
-9. I'm going to put it right here. -9. And then, so you did -9, and then you're going to do what? Subtract from that these 2 multiplied. So I'm subtracting -5?
Yep.
I'll even write subtract -5. I'll clean it up on the next line. Any questions on where I got that from? Are you good? So to get the first component of the cross product, you cover up the first column of numbers and you do the determinant on the others. What do you think I'm going to do to find the second component? Cover up the second column and do the determinant on the others. However, there's a catch. On the second one, you have to change the sign of your answer. So after you do the determinant, whatever answer you get, change the sign. Okay, so in other words, I'll do it like this. Whatever I get, I'm going to put a -1 in front of whatever I get. You only do that on the second one. Has anyone in this class ever had to do a determinant on a 3x3 matrix or a 4x4? You constantly have this like plus minus happening. That's what I'm accounting for here. Was there a question? No? Okay, so I'm going to cover up the second column and I'm going to do determinant on those. So I'm going to first do 2 times 3, which is 6. And I'm going to subtract from that 4 times 5 or 5 times 4, so subtract 20 from that.
Oh.
And then on the third one, you cover up the third column of numbers and you do the determinant, but this time you don't have to change the sign. So here we multiply this times this, we get -2. Then minus, now these 2 multiplied together are -12, right? So I'm going to have a negative. So my final answer is what? -4, because that's -9 plus 5. And then here, what do I get? 14. And then this right here, 10. And I have a new vector. And that is the cross product of those 2 vectors. You like dot product? Cross product?
I like dot product.
Dot product, right? Dot product is much easier to do, isn't it? But scalar multiplication is even better, right? So that's the mechanics, right? That's the mechanics behind the cross product. We'll have an opportunity to do more of it, but does anyone have a question on it? Yes?
Is that the same as matrices?
What do you mean matrices?
Like
The-
the cross product using the XY?
The cross product of a matrix?
I never learned matrices, so
Okay.
I was wondering if it was the same.
Well, there's a connection for sure because we're using like determinants here to figure out what the cross product is, right? But I'm not going to say there's a connection between what we're doing, like finding cross product, and like the type of determinant you're thinking about in a linear algebra sense. They are connected though, but the connection is, I think, beyond the scope of what we're talking about right here. Determinants come up, they're going to come up again later in this class. We're going to do something later when we're in three-dimensional space and vector spaces. We're going to be like converting from one space to another, like going from Cartesian to like a different coordinate system. And to do that, we have to scale everything. And to do that, we have to use this thing called a Jacobian determinant, which is more of this stuff. Yes?
Will there be an easier formula for cross product later on?
Have you ever seen an easier one?
I've seen it with like sine. That's it.
With sine?
Yeah, using sine.
Like sine and cosine? Is that what you mean? Or sine?
I don't want to like say it, but like, because I might misremember it, but it's like the magnitude, two vectors, sine theta, then some.
Oh, that. Okay, I know what you're saying. Now I know what you're saying. Yes, but it requires the angle between them. So it's just like, you know what, I'm about to show you the formula. You're about to see the formula, yeah. No, it's good, no, you're asking. But when you're given two vectors and you're asked to find their cross product, that's the mechanical thing, right? That's what you do. So what is this vector? Okay, so I've done it right here. This is a visual. It's not a very good visual, but I've got the two vectors that we just crossed. Okay, it was 2, -3, 5, and we did the cross product with the vector 4, -1, 3, and we got this answer -4, 14, +10. And I'm going to kind of move this thing around. Zoom in on a little bit. All right, so the black vector is the vector, that's the answer. You see it's in black? The blue vector is the blue vector, the red vector is the red vector, right? Do you all see that if I kind of rotate things around just appropriately, it looks like that black vector is, how is it related to those two vectors? It looks like it's perpendicular to which one, the red or the blue? Both. That is the property of that vector. That is the main thing about that vector. See, what we're doing is this. If you give me two vectors, okay, u and v, remember they're sitting in space, bring them tail to tail, and then take the u vector and cross it with the v vector, get your right hand out, put your fingers down the u vector, turn towards the v vector, because you're crossing u with v. Your thumb is going to be the direction of the cross product vector. So your cross product's going to come out like this, straight up, and it's going to be orthogonal to those two vectors. Every single time. Okay? Yes?
Does the length mean anything to that?
The length does mean something, yes. We'll figure out exactly what it means, today. I don't know about today, but we will very soon find out what the length of that vector means. All right? So that's, if I cross this vector with this vector, I use the right-hand rule, and my cross product comes out. It is orthogonal to both of these vectors, right? It points up like this. What if I did it the other way around, and I crossed v with u? What do you think would happen? I turn my hand the other way. I go right-hand rule v to u, and now the cross product comes down like this instead. So the only difference between that and this is a negative sign.
Would it be the negative sign on, I guess
It'd be the negative of the vector,
yeah, okay.
which points it in the opposite direction. That's the only difference. So remember dot product, it didn't matter u dot v is v dot u?
Yeah.
We could switch the order. With cross product, you can switch the order, but what happens is that the sign of the vector, or the direction of the vector changes, switches over. Now that's all written right here, okay? But let's get to one more thing here. Any questions on that? Look, I mean, this is pretty awesome if you think about it. I mean, we have a way of taking two vectors and finding a third one that's orthogonal to both. And believe it or not, that's going to be super helpful, super powerful. Yes?
So is that why you mentioned that if we do it like in R2, we have to expand to R3?
Wait, say again?
Is that why you said if we do it in R2, we have to expand it to R3?
Yeah, if you do it in R2, right, and if you're in two-dimensional space, you know, you have a vector that lives here, like let's say you take those vectors u and v, right, and you want to do a cross product. If you're on a flat sheet of paper, where's the cross product going to live? It's got to be orthogonal to both. So it's got to come out of the page at you, right? Which means all I would do, let's say that this was the vector 8, 2, okay? Let's say this was the vector, I don't know, 5, 4. Let's just say that's what it was. And I want to do a cross product. All I would do is say, no, that's the vector 5, 4, 0. And this is the vector 8, 2, 0. So now what I'm doing is I'm imagining that I'm actually in three-dimensional space. And then when I cross them, my answer can come out here. Yeah? All right. Show that when you cross a vector with itself, you get 0. The 0 vector.
Would you mind seeing it done a different way? Do you want to see the determinant?
Which way? What? This? That?
The determinant cross product. Not this question, but like done in a different way.
You can do this very easily after I give you a theorem here in a minute. I want this one done with us practicing the whole,
Yes, sir.
yeah. So I want to show that when you take u, any vector u, and you cross it with itself, you always get the 0 vector. So here's what I'm going to do. I'm going to start by defining u to be a three-dimensional vector, u1, u2, u3. Just like I did earlier when I did v1, v2, v3. And now I'm going to cross it with itself. So to cross that with itself, following the procedure that I just gave you, I would take that vector u1, u2, u3. I'd write the vector down. And then right below it, I'm going to rewrite it because I'm crossing it with itself. And then over here, I'm going to write the answer. U crossed with itself should be a three-dimensional vector, right? 3 components. How do we get the first component over there? Cover up the first column and determinant on this, which would be u2 times u3 minus u2 times u3. That's 0. Okay, is that going to keep happening? We go to the middle one. Remember, you have to put a negative in front of that, right? Okay, but does it matter? u1 times u3 minus u1 times u3. 0 again. And then finally, the last one, you can do it yourself. That's 0. If you get 0, 0, 0 in a vector, that's the 0 vector. Yes? Don't you automatically have I hat, j hat, k hat? Mm-hmm. Yeah?
Once you have that already here, or like, that's just common placement. You want to place it right here.
It's just a different notation for doing the same thing. I think what you're saying is instead of doing that, having I up here, j, k, is that what you're talking about? That's just a different kind of notation for doing, we're all doing the same operation.
Yes, sir.
Yeah. All right. So if you cross a vector with itself, you get 0?
0 vector.
0 vector. If you dot a vector with itself, what do you get? What's u dot u?
It's magnitude squared.
Magnitude of u squared, right? So take u, dot it with itself, you get the magnitude of that vector squared. You take u, you cross it with itself, you get the 0 vector.
Like, you can't be perpendicular to yourself. You
What are you referring to?
The direction of the perpendicular.
Crossing with your, when you take a vector and cross it with itself, right? So you take a vector u and then you put another copy of it right over, oops, sorry. And then I say cross them. You're supposed to get a vector that is orthogonal to both of these. But there's, which way are you going? Like, right? There's like an infinite amount, so that is just not defined. Like, it's defined to be the zero vector. The zero vector is the only vector that would be orthogonal, because to be orthogonal means that when you dot the two vectors, you get zero, right? So the zero vector would be the only vector that did that. All right. So now this question, and this is going to lead us very nicely into 10.5, which is coming. And I think 10.5 is where, I think I told you, this is where things start to get a little bit like, whoa, wait, hold on. How did all this happen so quickly, right? Look at this problem here. Find a vector that is perpendicular to a plane that goes through 3 points.
Don't like that.
So let's take a step back and just think for a moment. Let me get my three-dimensional space out here. I'm thinking of cutting part of these off, making them shorter or something. There we go, right? We have three-dimensional space here, right? We have 3 points, right? I'm giving you 3 points, wherever they are. Boom, boom, boom. If I give you 3 points in three-dimensional space, does everyone see that there is a plane, and only one plane, that goes through all 3 of those points? You have to see that first. So what do you need to define a line? You need 2 points, or you could say you need a point and a slope, but let's just go with points. How many points do you need to define a line? 2 distinct points, right? How many points do you need to define a plane? 3. So I'm giving you 3 points that create a plane. Sheet of paper right here, right? Somewhere this plane goes through all 3 of those points, somewhere. Ignore that it has x, y on it. Just, there's my plane, yes? What I'm asking you to find here is a vector, any vector that you can think of or come up with that is perpendicular to that plane. That's what you need. Understand? Mm-hmm. So, how do we do it?
Wouldn't you just cross all 3 of them?
Do what?
Wouldn't you just cross all 3 of them?
What do you mean by cross all 3 of them?
Oh, wait, cross.
So you have to be careful what you're given. Go ahead.
Yeah.
You can take one point and find the vector going to there and then the vector going to there, and that would be 2 vectors required to find the perpendicular.
Okay, exactly. So look, we have 3 points in space, right? Whatever they are. And we imagine a plane that goes through those points, right? A plane, but I'm just going to draw the triangle that lives on that plane, right? So I've got this plane here. That plane goes through those 3 points, right? The suggestion here is that what we do is we create a vector that goes from, well, this is not supposed to look like a right triangle. That was just the way I drew it, okay? I'm going to create a vector that goes from one point to another. Do you care which points? No, just any 2 points. I'm going to create a vector, and we're going to call that vector u. How do you create a vector between 2 points? From one point to the other, right? You subtract the coordinates, and then you create the vector, right? We did that at the beginning of last class. So you could do that, right? Because I've given you 3 points. And then you create another vector, like that. We'll call that v. So now in my picture, I've got a u vector here. I've got a v vector there, right? Like this. Got my 2 vectors that live on that plane. And then we cross them. So these 2 vectors live on that plane. And if I take those 2 vectors that live on that plane and I cross them, I'm going to get a vector that comes out like this. Or it might be the other direction, but either way, that vector will be perpendicular to that plane. Right? Right. There it is.
How did we go about creating the vector again? I don't remember that.
So let's say I wanted to create the vector that goes from there to there.
Yeah.
I would take -2, subtract 1. That'd be the first component.
Okay.
Then I do 5, take away 4. That'd be the second component. Then I do -1, take away 6. That would be my third component. That's my first vector.
Okay.
And then I need another vector.
So you just subtract
Yes.
the tail from the tip.
It's not tail and tip. It's 2 points. The
But
point
there
at the
would come a
tail,
tail in
the point at the tail,
Yes, the
and the point
tail
at the
from
tip.
The point at the tip.
Yeah.
Cool.
I just don't want to say you subtract points because we're not really subtracting points. We're subtracting the coordinates of the points.
Subtracting the values of the coordinates.
That's right.
At the
That's
tail
right.
and at the tip.
Exactly. All right, so you could create a vector maybe from here to here. Yes, you could handle that.
Yeah.
You could create a vector maybe going from here to here as well.
Easy.
Take those, cross them. Good? All right.
Yeah.
Try that on your own.
Let me write it down.
That's in your notes.
Okay.
All right, the next section in yellow, that, by the way, that is a very important skill to be able to do that. It's going to come up repeatedly in 10.5. We're going to need to be able to find a vector that is orthogonal to a plane. Do y'all need me to go through the actual mechanics or not? Show of hands. Do you want to see the whole thing worked?
That would be nice.
Yes? Yes? Yeah? See a couple, some of you are being shy. Yeah, no problem. All right, so I have my 3 points, right? I'm not gonna actually draw the points again. Well, maybe I will. So there we go. Got 3 points. Let's just label them. This is 1, 4, 6. This is the point -2, 5, -1. This is the point 1, -1, 1. Does it matter where I label those? No. Irrelevant, right? So now the vector you make is totally up to you. We just need 2 vectors on this plane. 2 different vectors. So I'll do the one that goes from here to here. I'm going to call that one U. So by the definition of how we create vectors, since I'm going from here to here, I'm going to take -2. That's the coordinate of that point up here, the x coordinate of that point. I'm going to subtract the x coordinate of that point, comma. Now I take the y coordinate of the first point, or the point I'm going to, subtract the y coordinate of the other point, and then -1, and then I take away 6. That will be my first vector, which I'm calling U. That good? Yeah? All right, now the other vector, anything I want. So I'll go, how about here to here? That okay with you? Do you have a question?
What you went from 1, -1, 1 to 1 plus 6.
You want to go here to here? Yeah, doesn't matter. You just have to have 2 vectors, because remember, once you create the vectors, you could always put them tail to tail, right? Because vectors float, right? So you could always move them tail to tail, and then when you cross them, you're still going to get a vector that's orthogonal. That's the beauty of vectors, that they're not fixed in a position. So once you define the vector, you can imagine it moving around. Yes?
Wait, you just said that you, what you did from the vector U, and then you then do the other way.
I can't do the other way.
Yeah, okay, I thought you just said that.
No, I think we said, right, you didn't say the other way like from here to here, right? No.
From that point to,
Yeah, he was saying from here to here. Yeah.
I
Yeah. Now you can't use the same vector, because then a vector dot across with itself would be the 0 vector. So, all right. So now to get V, right? V, which will be this vector here, I'm going to do. Since we're going to go from here to here, I'm going to go 1, take away -2, comma, and then I'm going to go -1, take away 5, and then 1, take away -1. Just be careful with your signs there. This should be 3, -6, 2. That's your V vector. Now, I'm going to cross them, right? Does it matter which order I do? Do I have to do U cross V, or can I do V cross U? It's not going to matter. All that changes is that, we have that plane, that flat sheet of paper here. And we got a vector. The vector that we get is either going to go like this, or it's going to come out the other side like that. Either way, that vector is orthogonal to the plane.
Okay, so when you say orthogonal to the plane, and there's 2 lines
there are an infinite number of orthogonal vectors to a plane. Because if you think about this, you've got the plane, not that it can move around, that I can change its length. See, like this vector, if I make it twice as long, it's still a perpendicular vector. Make it 3 times as long, it's still a perpendicular or orthogonal vector. So there are an infinite number of vectors that are orthogonal to the plane, but they all point in the same direction, or they're all parallel, I should say.
Yes.
They all go like that, or they come out the other side.
So wouldn't you say it would be all of them plus or minus all vectors? Does that make sense what I'm saying?
Well, we just need to find one vector, just one. And then any scalar multiple of that would satisfy it.
You could scale it by.
You could scale it by anything but 0. You can't multiply by 0.
Plus or minus vector would be the infinite.
Exactly. All right, so I'm going to do my shortcut here. I'm going to write down the first vector. I'm going to put the second vector below it. Right, that's just my setup so I can cover things up and do determinants like that. I should mention that most of you that have decent graphing calculators, the calculator will do a cross product. If you can learn how to input it properly, it'll do it. And on midterm, exam 1 and exam 2, final, I'm completely okay with you doing cross products on your calculators. Because to me, it's tedious. It's just busy work, all right? But you have to go learn how to do that on your own, or come to me and I can help you. Some calculators, you have to actually write a program to make it happen. If it's an older one like a TI-83 or something, there's a program. But I can even help you do that. It's not that hard. You could Google it. Yes?
So since we're not showing that work, would we cite it to say work on calculator?
Yeah, just did on calculator.
Okay.
Now, if it's wrong, that's on you. That's your user input error. But so double check it maybe.
So when you're doing the cross product, does the two vectors, do they have to share a tail? Like with that?
No. No, because remember these two vectors that live here, this purple and blue vector, right? I could just slide this one over like this, and now they're tail to tail, right? And when I say slide, I don't literally need to slide it because it's a vector, so I can imagine it was there to begin with, All right, it's a weird idea. Vectors are weird. All right, so look, I'm going to go. Here's my cross product, and I erased. Yeah, this one was U, and this one was V. So I'm actually going to do U cross V here. It's 3 things. And the middle one, I'm remembering, I'm going to put a -1 in front of it. So here we go. Determinant here, 2 minus negative 42. So 2 plus 42, 44.
Wouldn't it be 2 minus 40 because you're subtracting, and it's 2 negative, so it's...
Yeah, so this is 2, right? And then I'm going to subtract. What did we do? Did we add?
Wait, I'm
Hold on.
messing up.
No, I actually think you're right.
No, yeah, you're right.
It's 42. It's negative. No, yeah, it's negative 42 plus 2. It's negative 40. Yeah, negative 40. I'll put what we did. We did 1 times 2 minus negative 6 times negative 7. And that's what we did. 1 times 2. 1 times 2. So 1 times 2 minus 42. Let's see if we can get this other one here. That's negative 6. And then we're going to take away, so I'm going to write down negative 6, and we are taking away from that what?
Negative 21.
Negative 21. So that's 21, take away 6, that's 15, right? But then remember, there's going to be a negative in front of it. So 15 goes here, but there will be negative in front. And then the last one, 18, that one's, I think, straightforward. 18, take away 3. So 15. So a vector that is orthogonal to that plane is this. There we go. That is a vector that is orthogonal to that plane. Yes?
It's kind of a silly question, but could you reduce it?
I was actually going to suggest we do it. Like that is a vector that is orthogonal to the plane. but any scalar multiple of it is as well, right? So we could scale that down. What number goes into all those?
Except for 0.
5.
You can do 5, divide everything by 5? So what would happen if you divide by 5?
8,
Negative 8, negative 3, 3. That vector would work as well. You could also make that positive, positive, negative, multiply by negative 1. So any vector that you want, as long as it's a scalar multiple of that, yes.
So, I mean, I got a different answer. I did like a different set of points.
Okay.
Is it possible to have a different, like for your first value? Because I got 30, negative 15, 15. Is that possible?
Is yours a multiple of that? Like all of ours should be, your answer should be a scalar multiple of my answer.
Just in the lines.
Can you check if it's perpendicular by crossing it with any of the vectors? I mean,
Dotting it. Yeah, you can check your answer by dotting it with any of the vectors and you should get 0. There might be a mechanical error in there somewhere.
And then it wouldn't be orthogonal if you scale it by the 0 vector, correct?
Yeah, if you scale it by, if you multiply by 0, then now you have the 0 vector, right?
So that's
Which, the 0 vector is orthogonal to every vector. It's just not useful,
based.
right?
Yeah, that's true.
Because think about it, the 0 vector, is that orthogonal to any vector? Well, dot them. What happens if you dot this with any vector? What do you get? 0, and that's the definition of being orthogonal.
Isn't that technically, since you're at this point going to this point, it's a vector that goes in every direction simultaneously but has no magnitude?
If you wanted to, you could look at it that way. I mean, it's everywhere and nowhere. I mean,
It's basically it's a limit.
yeah. All right, we are almost out of time, but I want to put this up here because remember the other day I said I updated the notes?
Yeah.
Okay, I updated this section again. You don't need to go re-download it. These are basically formulas from straight out of the textbook, but I wanted to have them in my notes. This just gives us all the properties of the dot product, the cross product, in terms of like U cross V is the same as taking V and crossing with U. So you switch the order and the only difference is that you get a negative. So it changes the direction of the vector. And then there's a bunch of other properties that involve like scalar multiplication, and this is like a distributive property of the cross product over addition, and then some sort of like weird associativity properties. So just know that these properties exist. If we need them later, I will refer to them. Like I'll come back and say, hey, let's go look at those properties. Let's use that one property. We don't use these a lot, but we just need to know that they're there, all right?
All right.
And then that will leave me at a good place for us to just look at this, and then we can continue this next week, right?
Yeah.
Wow, okay. All right, so the theorem, remember we had the theorem for dot product. For dot product, we said if you take U and you dot it with V, it's the same as taking the magnitude of U, magnitude of V, cosine of the angle between. That was from last class, dot